Hello guys, we are back to continue projectile motion now in part 2 problems. In previous video we got the lessons. I hope you have watched the video, but anyway, the link of the video is in the caption. You can watch it first and then continue. But if you are ready, let's start. Number 1, an object is thrown from the ground with a speed of 18 meters per second at an angle of 30 degrees to the horizontal in absence of a resistance. I take the coordinate system yx like that, and then I threw the object from the origin with the speed of 18 meters per second, making an angle of 30 degrees to the horizontal. So the velocity will have the magnitude of 18 at the beginning, and then the angle it makes with the horizontal is 30 degrees. Find the components of initial velocity. Components means Vx and Vy. So I should decompose this vector. If I decompose that, you know that the horizontal will be V naught cosine of 30 degrees, and this vertical will be Vy V naught sine of 30 degrees. Basically, as the V naught has the magnitude of 18, so I plug in the values. 18 cosine of 30 degrees. Cosine of 30 is going to be square root of 3 divided by 2. So if I multiply 18 by square root of 3 divided by 2, I will get 9 square root of 3 meters per second. This is the horizontal component of the initial velocity. Vy, likewise, will be 18. Sine of 30 degrees, sine of 30 degrees will be a half. So it's a half of 18, 9 meters per second. Part B. Find the speed at the peak point. Peak point is here, is where the object won't go anymore to the vertical direction. It will lose its vertical component of the velocity. So Vy must be 0. No vertical displacement anymore at that point. So I will just have the horizontal component of velocity 9 square root of 3 meters per second. This is the velocity at the peak point. Why it won't change? Because in absence of air resistance, basically we expect the horizontal acceleration to be 0. There is no force acting on the object in horizontal direction. So it will keep the same horizontal velocity, horizontal component of the velocity to the end of the trajectory. Just the Vy is affected by the vertical force of the gravity. So we have just vertical acceleration. This is why not only in the peak point, in every other point, the horizontal component of the velocity will be the same, 9 square root of 3. The difference is that at this point, for example, we will have also a vertical downward Vy. This is why the velocity at this point will not be exactly 9 square root of 3. But at the peak point, as we don't have any vertical component of the velocity, we expect the horizontal will be the only component we have, 9 square root of 3. Number 2. An arrow is fired horizontally from the top of a tower 35 meters above the ground. Guys, pay attention. At the beginning, the object is here, 35 meters above the ground, but it is thrown horizontally. Horizontally means that initial velocity is horizontal. And so if it is horizontal, basically we have no theta. So initial angle for the velocity to the horizontal is 0, theta naught or theta. It's the initial velocity. So the object will fall down. There is no peak point anymore. The peak point is basically the beginning point. Assume that air resistance is negligible. Okay, it's something we always do. The G is given to be 10. Calculate A, the time for which the arrow is in the air. How to find that? Let's check what are the quantities we know and what's the goal, what's the quantity we're looking for. The quantities we know, one of them is delta Y, which is going to be negative 35. Negative 35 because the beginning point and the ending point make an arrow downward. You know that displacement is a vector starting from the beginning point and ends at the ending point, downward. It is downward here, so delta y is negative 35. Also, I know the acceleration, I know the theta, and I know the initial velocity. which is 30. So it's good. I'm looking for t. So let's make a relation between, or find a relation between these given quantities and the goal, the time. The best, I think, is the position time or displacement time relation. Delta y equals v naught sine of theta times t minus a half of gt squared. Okay, here we are very lucky. Sine of theta is 0 because theta is 0. So forget about the first term. Delta y is negative 35. I told you because the object is coming down, falling down. Delta y is negative. And negative a half of 10 t squared. 10 is replaced for g. I think that t squared to be 2 times 35 divided by 10. So it is 7, and so t is square root of 7. It's estimately 2.6 seconds. This is the first part, part A. Part B. The distance from the foot of the tower at which the arrow strikes the ground. Distance to the foot means that we are looking for the displacement of the object from here to here, horizontal displacement. Let's say it's delta x, okay? So I'm looking for delta x. Just remember, horizontal motion was a non-accelerated motion. It was a uniform motion. Why? Because in horizontal direction, there is no force acting on the object. So delta x must be very easily vt, and it's v naught t, because horizontally the velocity will keep the same value as the beginning all around the journey. So this trip horizontally will have a horizontal velocity of 30, so it's uniform motion, delta x v naught t. Let's substitute the values. You know that the t comes from the previous part. I know it's about 2.6, and so if I plug in the values, I will get 78 meters. This is the horizontal displacement. Just, I should remind you that the whole displacement is not delta x and it's not delta y. But the displacement really is an arrow connecting the beginning point and the ending point, the total displacement. So it's, let's say it's d. If you are going to find the d, you should write d is equal to, let me write it here on a blackboard. D is going to be square root of delta x square plus delta y square. This is something you should look for. So of course, it's not our goal here. I just added. The part C, the speed at which the arrow strikes the ground. This speed is the magnitude of the velocity. You know, at the point when the object strikes the ground, horizontal component of the velocity is the beginning velocity, the initial velocity is 30, you know. Also, it will have a vertical component like Vy. And if I know the Vy, this is the velocity. I'm looking for a speed. So speed will be magnitude of that. So it's square root of Vy square plus Vx square. I know the Vx, just I'm looking for Vy. So if I find the Vy, I can complete the task. How to do that? For Vy, I know that, of course, I have two alternatives. I know that, first, the total time of this journey is about 2.6 seconds. G is also 10. So it's the easiest way to use this equation, Vy equals v naught sine of theta minus gt. As sine of theta again is 0, because the vertical component of the velocity at the beginning is 0, so Vy will be negative gt. That's all. Let's just plug in the t to be 2.6 and get negative 26 meter per second. This is the Vy. Now I will find the, let's say, the resultant vector. Basically, it's the horizontal and it's the vertical component, so v is a resultant. So it's square root of 30 squared plus 26 squared. And the answer will be 40 meters per second. The other alternative for finding the Vy will be the time-independent equation. Vy square minus 0 square, because Vy at the beginning is 0, is equal to negative 2g times delta y. And delta y is negative 35. So Vy square will be negative 2 times 10 times negative 35. If you want, you can use also this equation to find the same value. When you take the square root from Vy, pay attention basically, as the Vy is a negative quantity here, as it's downward, you should choose negative 26, not positive 26. But of course, for finding the V, it is not that matter. It's not that important. Okay, this is number 2. Let's go to number 3. An object is thrown horizontally from a ship and strikes the sea 1.6 seconds later at a distance of 37 meters from the ship. It starts like that. The theta, the initial angle, is 0, and the velocity is all horizontal at the beginning, and it will strike the sea level 1.6 seconds later. So t is 1.6 seconds. Part A, calculate the initial horizontal speed of the object. So I'm looking for Vx. And part B, the height of the object above the sea when it was fired, thrown. Here also the G, as usual, is given to be 10. If even they don't say anything, please neglect the air resistance. Okay, here I am also looking for the vertical displacement h, and we know that the horizontal displacement of the object is 37 meters. How to find it? I have two alternatives. First is using equations. Look at that. Vx is all constant. You know that horizontally the object does not have any acceleration. Ax is 0 because the object is just acted by the vertical downward pull of the gravity. So I expect delta x to be Vxt. That's all. You know, delta x is something I know is 37. Vx I'm looking for, and t is 1.6. That's all. So I can find here the Vx. And for the h, I can use this equation. I can write, let's say, h is equal to negative a half of gt squared and plus 0, because vertically the velocity at the beginning is 0. So as it is v naught sine of theta times t, sine of theta is 0. So forget about the second term. That's all. And moreover, I know that the displacement is not h, but the displacement is negative h, okay? Because it's downward. So here I should put negative sign here. And as I know the t, it is 1.6, I can easily find the h. The other alternative is using graphs, VT graphs. Also, it may be somewhat attractive for you, as mostly you don't use that. So let's start from Vx. As you know, the horizontal displacement is a uniform motion because we don't have any horizontal acceleration. So if I have a Vx at the beginning, I will keep the same Vx to the end of the journey. So it's constant. 1.6 seconds later, the journey is done. So it is not going to be more than that. So the total area under the graph will give the total displacement, but horizontal displacement, because it's Vx. And so the area under the Vxt graph will be delta x. So it's 37. I know that. Okay, look at this rectangle. You see the horizontal side is 1.6, vertical side is my goal, Vx, and the area is 37. So it's very easy to find 23. This is the Vx. So basically I write 37 is equal to width times length. So it's 1.6 times Vx. That's all. The other is using the Vyt graph. You know that Vy at the beginning at t equals 0 will be 0 because the object is thrown horizontally. So horizontally there is no vertical velocity component at the beginning. So Vyt will be a graph like this, a descending line, and the slope of this line is G, of course, negative G, here negative 10, you know, and the total journey will take just 1.6 seconds, not more. As the slope of this graph is 10, slope is 10, basically I expect vertical over horizontal to be 10. So I believe that if this is Vy, vertically it's Vy, when it strikes the ground or the sea level is Vy. So here I have a Vy, the vertical side, and the horizontal side is 1.6. Slope is 10. It's rise over run. So it's Vy divided by 1.6. So Vy is 16. 1.6 times 10. So here I put negative 16. Basically, it's downward. So Vy is negative 16 meters per second. Then I will look for h. H is the total displacement. So it's the area under the graph here. Very easy. So it's h. How to find the h? Let's say height times base divided by 2. Mathematically, this is height of the triangle, which is 16. Now forget about the negative side. And it's 1.6 for the horizontal side. So h will be the area under the graph, which is 13. H is 1.6 times 16 divided by 2. This is another alternative. You know that when I use VT graphs, I'm basically using the origin of the equations, because equations are all coming from the source of the VT graphs. So the graph is the same as equation, but in my opinion, it can carry more conceptual understanding for you, as it provides a more wider view, for wider perspective for the people who are learning the kinematics. But of course, you are free, you can use both of them. A ball is thrown at an angle of 30 degrees to the horizontal from the ground at a speed of 20 meters per second. Calculate its range and the maximum height reached. Okay, the whole perspective of the motion is like that. The velocity at the beginning makes an angle of 30 degrees to the horizontal, and the initial speed is 20 meters per second. What's the range and what's the maximum height? Range basically is the total horizontal displacement of the object, and it's ground to ground, okay? It's range. And vertically, the object will get a pitch point like that, so it's the maximum height reached. Let's look for both of them through the graph approach. Graph is easier to understand. First, let's look for the components of the velocity. The horizontal component of the velocity at the beginning will be v naught cosine of theta. So it will be 20 times cosine of 30 degrees. And you know that cosine of 30 degrees is a square root of 3 divided by 2. So it's 10 square root of 3. And if I take the square root of 3 to be almost 1.7, seems to be almost 17. So I take the horizontal component of the velocity at the beginning to be 17 meters per second. Then I continue for vertical component. Vertical component will be Vy at the beginning, V naught sine of 30 degrees. V naught is 20, so it's 20 times a half. The sine of 30 degrees is a half, so it's 10. Vertically 10. Then I draw VT graphs. Vyt will give me the time and also the vertical displacement, because h is related to delta y, so it's found in Vyt graph. And the horizontal displacement r is a kind of delta x, so it's gonna be found in the Vxt graph. For Vyt, I start from the vertical initial velocity component of the velocity, which is 10 meters per second. So it will be 10, and then it's the descending line with the slope of 10. Basically, the slope is the acceleration, 10. Okay, here is the our VT graph, VYT graph. But there are a lot of things to be easily seen here. First is this time. This time is the time at which the object will get the peak point. So it's corresponding to that point. How to find it? You remember that the slope is height over base, or rise over run. Here rise is 10 and run is t. Let's say that moment is t. So slope will be 10 divided by t. On the other hand, I know that the slope is 10. So t will be 1. Very easy. This is the what t equals 1 second, the time at which the object will get the peak point here. As it is a symmetrical trajectory, it's ground to ground, the time from here to here will be equal to the time from here to here. So when the object again strikes the ground, the total time will be 2. It's the total time of the journey. Now I'm going to find the vertical displacement from the beginning to the peak point. It's exactly h. How to find the h? It's the total displacement here, the area under the graph. Very easy. So it's delta y from 0 to 1 second. So it's delta y seems to be exactly the same h. Delta y is 10 times 1 divided by 2, the area of the triangle. So it's 5. So here I can say the vertical displacement to the peak point is 5. So totally the object will get maximum height of 5 meters. To continue for r, I should look for a delta x. So I should draw the vxt graph. Vx is all constant. You know that acceleration in horizontal direction is 0. The object is not acted by any force in horizontal direction. So Vx starts from 17 meters per second and it is continued to the end of the journey. Of course, the end of the journey is just 2 seconds. Now the total displacement of this object, which is called range here, is going to be the area under the graph, Vxt graph. So it's a rectangle. Easily I can multiply 17 by 2 and get the result. It's 34. So range is 34 meters. Number 5. It's very similar question to the number 4. I'm just repeating the new one just to emphasize on the concept of VT graphs. It's very useful to repeat the same scenario again. Calculate the range of a projectile thrown from the ground at an angle of 60 degrees to the horizontal with velocity of 30 meters per second. Very similar question. G is given to be 10, and also we neglect any air resistance. I am looking for the range from here to here. I told you range is the displacement of the object in horizontal. How to do that? I used VT graph. VT graph will be a horizontal line because the horizontal velocity is constant, I told you, and it starts from the horizontal component of the velocity. It's going to be V naught cosine of 30 degrees. V naught cosine of 30 degrees will be 30 multiplied by cosine of 60 degrees. Cosine of 60 is a half, so it seems to be 15 meters per second. So it's 15. It starts from 15, continues with 15. I'm looking for the total displacement in horizontal direction, which is called range here. But the problem is that finding this range needs necessarily the total time of this journey. And I can't find the time through this graph. What should I do? I should again continue with VYT graph, find the total time of the journey from VYT, and then substitute the t here to find the total horizontal displacement. Vy. Vy starts from the vertical component of the velocity. Vertical component of the velocity at the beginning is V naught sine of theta. V naught sine of theta is 30 times sine of 60 degrees. So it's 30 times square root of 3 divided by 2. So it's 15 square root of 3. Let's say square root of 3 is about 1.7. So it's almost 26. So Vy will start from 26 and it's a descending line. You know the slope of this line is the acceleration, which is 10. Of course, negative 10, but the magnitude is 10. Then I continue to find the time. Here for finding the time, this time is exactly the time of the peak point here. It's time of here. And the end is here corresponding to this moment. Okay? I'm looking for the peak point first. The time for the peak point is very easy here. Let's use the concept of the slope. Slope is rise over run. Okay, rise is 26, run is t, and the slope is 10. That's all. So t is going to be 26 divided by 10, which is 2.6. 2.6 is the total time to get the peak point. As it's symmetrical, ground to ground trajectory, so I expect the same time from the peak point to the ground. It's again 2.6 seconds. 2.6 plus 2.6 will be 5.2. It's the total time of the journey. So I can easily plug in 5.2 here. It's the total time of the journey in horizontal direction also. Now, the area under the graph, which is the range. That's all. How to find the range? 78. How? 78 is equal to exactly 15 times 5.2. That's all. This is the range. Let's continue for a different case. Number 6. A gun is aimed so that it points directly at the center of a target 200 meters away. This is the gun, this is the target, and it's separated for 200 meters. If the bullet is shot at 200 meters per second, so initial velocity is 200 meters per second, theta is 0, it's horizontal projection. How far below the center of the target will the bullet hit? I am looking for the vertical displacement of the bullet during the journey. Normally, you know that the bullet, rather than the horizontal displacement with constant speed of 200 meters per second, also it will have a vertical accelerated motion, and so it will have a displacement of delta y. How to find the delta y? It's very easy. You know that delta y is the area under the graph of vyt. Vyt graph will be a descending line because the slope is always 10 or 9.8, whatever, but negative 10. So it's a descending line. Why it starts from 0? Because vertically at the beginning, theta is 0. So Vy will be V naught sine of 0. So it's 0. We don't have any vertical component for velocity, so it starts from 0. On the other hand, Vxt will be always a horizontal line, starting from 200, and it is continued with the same value, because 200 is always constant. Horizontally, the object has no acceleration. Okay, here I am looking for delta y. Basically, delta y is the area under the graph in Vyt graph. But the problem is this t. I don't know this t. Let's find the t from the Vxt graph, then plug in the t here and find the delta y. This is the path. So I start from the area under the graph. Vxt will have the area of the under the graph of 200 meters. Why is that? Because it's delta x. The area under the Vxt is delta x, 200. So I know that it's 200. Look at this rectangle. Here, vertical side is 200, so it's 200 equals, it's 200 times the horizontal is t times t is equal to area 200. Again, 200. So it's very easy. 1 second. So it takes 1 second for the bullet to get the target. Now I can use the same 1 second here in Vyt graph, and then the area under the Vyt graph to be the vertical displacement, delta y. I know that this side is 10. Why is that? Again, let's go back to the concept of the slope. Slope of this line is 10. So 10 will be rise. Let's say rise is Vy over run. Run is 1. So Vy will be 10. This is why I put 10. But you may have objection. You may say, oh, sir, this is a problem. It must be negative 10 here. Oh, I know that, but it is just the magnitude. Forget about that negative sign here. doesn't matter really because I'm just looking for the area under the graph, negative or positive. This is just the absolute value of this delta y, magnitude of that. So it's very easy. Let's say delta y to be the area under the triangle here. Horizontal side is 1, vertical side is 10, divided by 2, so it's 5. So the vertical displacement for the bullet when it gets the target will be 5 meters, of course down. Number 7. An object is thrown horizontally with a velocity of 12 meters per second. Like that. So theta again, the beginning is 0. Determine A, the vertical component of velocity after 4 seconds. Vertical velocity of the component of the velocity at the beginning is 0. You know, Vy at the beginning is 0 here. But after 4 seconds, no. Because vertically the object is accelerated for 10 meters per second square, so it will increase and increase and increase. Let's go back to the concept. You remember that if the acceleration is 10 meters per second square, so I expect that for each second, delta Vy, change in velocity in vertical direction, to be negative 10 meters per second. This is why we say the acceleration is 10 meters per second square. Basically, it's 10 meters per second every second. So it's 10 meters per second in each second. So if I wait for 1 second, delta V in vertical direction will be negative 10 or 10. So after 4 seconds, it will be 4 times 10. Each second, it gains 10 meters per second. So the other 20, the other 30, and the fourth second, it will be 40 meters per second. Of course, it's downward, so all vertical components are going to be negative values. So let's say it's vertically negative 40 meters per second. Of course, if you use the equation, you will get the same result. Part B. The x and y components of the position vector of the object after 4 seconds, delta y and delta x. For delta x, it's very easy. You know that delta x is all a horizontal uniform motion because ax, horizontal acceleration, is 0. The object is not acted by any horizontal force. The force is just vertically acting on the object, which is the gravitational pull. So ax is 0. So the object will displace for 12 meters in each second in horizontal direction. Why? Because we know that 12 meters per second means 12 meters in each second. As it takes 4 seconds in this journey, so it will be each second 12. So 4 seconds, 4 times 12. So we expect 48 meters for horizontal displacement. But vertically, it's not like that. Vertically, it's accelerated. I can use VT graph in vertical direction, or you can use delta y to be negative a half of gt squared. Of course, it has another term which is not necessary to write. It's v naught sine of theta times t. You know that sine of theta at the beginning is 0, so no need to add such a term here. So I should just continue to plug in the values. It's negative a half of 10, g is 10 here, t squared, 4 to the power of 2. It is 16, 16 divided by 2 is 8, so it's 80. Basically, it will displace for negative 80 meters downward. Negative because delta y is a vector downward. Number 8, a projectile is launched at 30 degrees to the horizontal with initial speed of 24 meters per second, like that. Determine the maximum height reached. Maximum height reached is here, at the peak point. It will have the maximum height and the corresponding time, the time of that. We have different alternatives for that. This time, I'm going to use the time-independent equation. Vertically, you can write Vy squared minus V naught y squared is equal to negative 2g delta y. Yes, you can use it. And so I know that at the peak point, vertical velocity will be 0. As I can find the vertical component of the velocity at the beginning, I can find this value. I know that. And so g is given here. So I will find delta y to be this h. It's very easy. So let's do it. Again, I emphasize that at the peak point of velocity vertically will lose its component. So it's 0. Vertical component of the initial velocity is Vy, V naught y. V naught y is a vertical component, so it's 24 times sine of 30 degrees. V naught sine of 30 degrees. 24 times sine of 30 degrees is a half, so it's 12. It's 12 meters per second. Vy is 0. Here, 12 raised to the power of 2 is 144. Negative 2, g is 10, and h. That's all. So you can easily find h. H is going to be 144 divided by 2 times 10. Here I have 14.4 divided by 2, so it's 7.2 meters. For the time, it's very easy. I can use the vertical velocity time equation. Vy will be v naught sine of theta minus gt. It's very easy. So let's use it. But at the peak point, Vy is 0. This is why here I put 0 instead of Vy. T is my goal. V naught sine of 30 degrees is totally 12 meters per second. So it's going to be negative 10t plus 12 equals 0. So t will be 12 divided by 10, 1.2 seconds. Number 9. A projectile is launched horizontally with initial speed of 20 meters per second. Okay, it's like that. Horizontally, so it's the theta at the beginning is 0, so it's thrown just with horizontal component of the velocity at the beginning. V naught at the beginning is 0. How many seconds it takes that the speed makes an angle of 45 degrees to the horizontal? So let's say the vertical fall will be very, very long, so it has enough time to get 45 degrees of angle to the horizontal. How to find that? Let's check the situation. Suppose that after a few seconds like t, the object will get at this point. And let's say the velocity at the horizontal is the same, because you know that ax, horizontal acceleration, is 0. So it's the same Vx, but Vy is something I don't know. But I emphasize that there is a velocity as a vector like that, which makes an angle of 45 degrees to the horizontal. If it is 45, triangle with 45 degrees, a right triangle with 45 degrees, let's say it's 45. As it is 90 degrees, it must be also 45. So it's also an isosceles triangle. So vertical and horizontal sides are equal. As the horizontal side is 20, vertical also must be 20. So here I expect Vy to be 20 meters per second. So basically, it is hidden in this problem that when they say 45 degrees for the velocity, they emphasize on the equal values for the components, horizontal and vertical components of the velocity at that point. So it's 20. Of course, this negative sign is just to emphasize that it's downward. Okay, so basically they ask you how many seconds it takes that the object gets negative 20 meters per second in vertical direction. Just remember the g. G is 10 meters per second squared. So in each second, the velocity in vertical direction will increase for 10 meters per second. If you need 20 meters per second, so you should wait for 2 seconds. That's all. It is done. So after 2 seconds, the object will get this point. The vertical component of velocity is 20, is equal to the horizontal velocity component, and so it makes the 45 degrees of angle to the horizontal is the velocity. That's all finished. Thank you very much. This video is done. Thank you for being with me. I'm really grateful to you. Please again from the beginning, solve all the questions for yourself, review the lessons, and then confirm your understanding. Kinematics needs just practice and practice. Thank you very much again. See you.